This explosion got slower the farther away it was. That's not a camera glitch, it's the mystery. Why does a Type Ia supernova look like it's unfolding in slow motion across cosmic distances? Two identical kinds of stars, same physics, but the far one's explosion takes 1.5 times longer to peak than its twin. How does distance act like a cosmic slow motion button? Astronomers use these explosions as cosmic clocks. Type Ia supernovae have reproducible brightness curves, so when one runs slow, either something's warped our measurement of time, or we're missing a cosmic twist in the clockwork. We already know redshift stretches light by 1 + c, but if expanding space lengthens photons, shouldn't the intervals between each tick, each moment of a supernova, get stretched too? Or is this all an illusion? Instrument schedules, rough weather, mismatched camera filters, even the supernovae's inherent quirks, any of these could fake a slower light curve, a well-timed trick of the cosmic game. Astronomers remapped colors to match the source's rest frame and erased known quirks, leaving one thing to test. After all corrections, is there still extra stretch, something beyond astrophysics, stamped right into the data? Early hints appeared. Supernova durations grew systematically with redshift, roughly matching the 1 + c scale. But with so few explosions, it still could have been a cosmic fluke lurking in the noise, stakes rising with every new observation. Light curves might fool us, but spectra evolve at their own pace. So do distant supernova fingerprints delay their changes too, ticking through spectral time in a 1 + c stretched slow motion? By the late 1990s, two teams, rivals, kept adding distant explosions. Different telescopes, but the pattern never broke. The farther the blast, the more time stretched. If this was a fluke, it was a stubborn, universal one. Dust can dim explosions. Stellar evolution might nudge their color, but neither can slow every cosmic clock by 1 + c. With other suspects ruled out, one explanation remains: something stretching time itself. At redshift 0.5, supernova clocks genuinely tick about 1.5 times slower. Even the spectral aging test matches this stretch. Goldhaber and team pinned it down. The universe's time stretch is real, not random error. Gravitational lensing does weird things. It can amplify brightness, but not universally stretch cinematic time. No matter how big the cosmic magnifying glass gets, the movie's duration stays true. Hundreds of supernovae solve the case. Every distant explosion's light curve stretches by exactly 1 + c. It's direct visual evidence, cosmic time dilation, painted onto the data, proof the universe is expanding. As the universe expands, every gap grows, between photons and between moments in time. Stretched light equals stretched time. The redder the glow, the slower the cosmic clock. Two sides of the same expansion. That slow-motion supernova story became a cornerstone of modern cosmology. This time dilation alone, without any twist about accelerating expansion, stands as a direct empirical sign of an expanding universe. Across the universe, it's always the same rule. The farther you look, the slower cosmic clocks tick. Flares, flickers, and blast waves, all stretched out, taking their cosmic time to finish the story. Now, with new surveys like DES and LSST, astronomers watch thousands of distant explosions. If there's any tiny crack in the time dilation test, these new cosmic factories will catch it. The stakes keep growing. A distant blast slowed down and proved space itself is stretching, right before our eyes. You now understand something most science textbooks leave out. Hit subscribe. The next discovery is already waiting.